This problem focuses on understanding how combining different kernel functions in Gaussian process regression affects the model's ability to capture relationships in data. I'll be looking at how a composite kernel, formed by multiplying an RBF kernel and a linear kernel, behaves. It's all about understanding the math behind the kernels and what properties they bring to the model. The radial basis function, RBF, kernel is one of the popular kernel functions. It models smooth, nonlinear relationships in data. The length scale parameter, here, 2, controls how smooth the model will be. A smaller value means more localized, wiggly relationships, while a larger value creates smoother relationships. The linear kernel is simpler. It directly models linear relationships between the input and the output. Think of it as modeling a simple straight line. Here, I'm combining the RBF and linear kernels using a product. This means the combined kernel's behavior will be a blend of both. I'll be looking at how their product affects the model's ability to learn from data. This is the core question. I need to determine which statements correctly describe the combined behavior of the RBF and linear kernels when they are multiplied together in a Gaussian process regression model. I'll analyze the options one by one. This option is partially correct because the composite kernel will indeed model smooth, RBF part, and linear trends, linear part. However, the periodic aspect is incorrect. Neither base kernel has inherent periodicity, so their product won't magically introduce it. Let's keep moving. This is the title for the question in the quiz. This describes the overall machine learning method I'm using. Gaussian process regression, with a composite kernel function. The composite indicates that I'm combining different basic kernel functions to create a more complex model. This indicates that the core components of the composite kernel are being introduced. This statement is correct. The composite kernel is more flexible since it can capture both linear and nonlinear patterns in data simultaneously, unlike the single kernels, that can only handle either linear or nonlinear patterns alone. This is incorrect. The combination of kernels, whether through addition or multiplication, as in this case, never equals just one of the kernels alone. The resulting kernel has different properties. This statement is wrong. A large length scale in the RBF kernel will make the RBF component appear almost flat, a constant function, reducing its nonlinear influence. However, the linear component will still exist and play its role. The linear part remains unaffected. This is the question we need to answer. We're asked to determine what a composite kernel, a combination of a radial basis function, RBF, kernel and a linear kernel, can do. This sets the stage for evaluating several statements about how this composite kernel will work. This option suggests that the combined kernel handles smooth curves, repeating patterns, periodic, and straight lines. I need to check whether that's true based on the properties of RBF and linear kernels. Let's see. This option proposes that combining the kernels increases the model's ability to fit various kinds of data. This is what I'm hoping is true. I'll determine whether combining these kernels grants additional power. I'm asking you to analyze how combining an RBF kernel, modeling smooth, nonlinear relationships, and a linear kernel, modeling linear relationships, using a product kernel affects the overall model's ability to capture different patterns in data. The product kernel multiplies the effects of the base kernels together, creating a new kernel which is more expressive than either base kernel on its own. This statement is partly correct. The combined kernel can indeed capture smooth, from RBF, and linear trends, from the linear kernel. However, it doesn't magically introduce periodic relationships. Neither of the base kernels inherently model periodicity. This is absolutely correct. Because the product kernel combines the strengths of both, it can capture a wider range of relationships than either could alone. Think of it like having both a hammer and a screwdriver. You're much more versatile than if you only had one. Absolutely not. Combining kernels using a product fundamentally changes the kernel's behavior. It's not simply a case of one kernel overriding the other. The resulting kernel is a completely new entity. Incorrect. A very large length scale in the RBF kernel makes it behave like a constant, effectively minimizing its nonlinear influence. However, the linear component still remains. The kernel will still capture linear relationships, the nonlinear aspects are just suppressed. I use Gaussian process regression, a powerful machine learning technique, to predict continuous values. It's like drawing a smooth curve through data points, making predictions about where the curve goes between known points. It leverages the concept of kernels, which we will explore further. This is the core question. I am testing your understanding of how combining kernels affects predictions made by GPR. We need to explore how each type of kernel works. I create a combined kernel by multiplying the results from the individual RBF and linear kernels together. This means, I am combining their effects to capture both linear trends and smooth curves within the data. This is a radial basis function kernel. I use it to model smooth, nonlinear relationships in data. The length scale parameter, set to 2 here, controls how far-reaching the influence of each data point is. A smaller value means local effects, while a larger value leads to smoother, more global effects. I use a linear kernel to model strictly linear relationships in data. I represent these relationships as a straight line. It directly captures relationships proportional to input variables. I combine the RBF and linear kernels. The overall composite kernel captures both linear and nonlinear behavior, resulting in a more flexible model than either kernel alone. The composite kernel will indeed model both smooth relationships from the RBF and linear trends from the linear kernel, but there is no periodicity. Adding the kernels does not automatically produce periodic behavior. This is correct. By combining both kernels, the combined model is more flexible and can capture a wider range of relationships in the data. This is wrong. Combining the kernels through multiplication fundamentally changes the resulting model. It will never be identical to either of its components. This is also incorrect. A large length scale in the RBF kernel makes it behave more like a constant, weakening its nonlinear influence, but the linear component from the linear kernel will still remain. This question asks you to think critically about how combining different types of kernels in Gaussian process regression, GPR, affects the model's ability to capture patterns in data. We're specifically looking at how a product kernel, which combines a radial basis function, RBF, kernel and a linear kernel, behaves. This option is partially correct. The composite kernel can model smooth relationships, because of the RBF kernel, and linear trends, because of the linear kernel. However, it doesn't magically create the ability to model periodic relationships, which neither base kernel inherently does. So, it's a bit of an overstatement. This is the correct answer. By combining the RBF kernel's ability to model smooth, nonlinear relationships with the linear kernel's ability to model linear trends, the composite kernel becomes significantly more powerful. It can handle a wider range of data patterns. Think of it like this: an RBF kernel is like a brush with soft bristles for smooth curves, and the linear kernel is like a ruler for straight lines. Combining them gives you both tools, making the model far more versatile. This is incorrect. Combining kernels using a product kernel fundamentally changes the model. The resulting kernel's behavior is not simply the same as using only one of the base kernels. It's a completely new beast. This is also wrong. A large length scale in the RBF kernel makes the RBF part less influential, kind of like blurring the nonlinear aspects. However, the linear part from the linear kernel remains fully active and will still be used by the model. The linear modeling capability will not disappear. This tells us that we are using a special type of machine learning model called Gaussian process regression, and it uses a composite kernel, meaning it's a combination of several kernels. One of our base kernels is a radial basis function, RBF, kernel. This is a type of kernel that often creates smooth, bell-shaped curves. The length_scale parameter controls how wide or narrow these bells are. A value of 2 indicates a moderate width. Another base kernel we are using is a linear kernel. This kernel is best suited for modeling data that shows a clear linear relationship. It's the simplest kernel in the bunch. It draws straight lines. This is how we combine the RBF and linear kernels. The product kernel takes the element-wise product of the covariance matrices from the RBF and linear kernels. This combines their strengths to create the final composite kernel. The result of using the product kernel is a model that can capture both the smooth, nonlinear trends modeled by the RBF kernel and the linear trends modeled by the linear kernel. I see that RBF stands for radial basis function. This kernel creates a smooth, curvy relationship between your data points. The length_scale parameter controls how far the influence of each data point extends. A smaller length scale means the curves are tighter and more localized. A larger length scale leads to smoother, broader curves. Think of it like drawing. A small length scale is like using a fine-tipped pen to create detailed curves, whereas a large length scale uses a broad marker for smoother lines. A linear kernel creates a simple straight-line relationship between data points. It's the simplest type of relationship. If your data follows a straight line, this is your kernel. The product kernel takes two other kernels, like our RBF and linear kernels, and multiplies their results together. Imagine it like combining the drawing tools I described before. The product kernel lets you have both straight lines and curves in your model, making it much more flexible than either kernel on its own. It's like being able to draw both precise details and sweeping lines at the same time. Since the product kernel combines a linear kernel, straight lines, and an RBF kernel, curves, it can capture data that has both straight line trends and curved patterns simultaneously. This flexibility allows for a more accurate fit to complex data. It's like having a toolbox with both a ruler and a flexible curve. You have the right tool for every aspect of the job. I disagree with this statement. Combining kernels using a product kernel results in a different model than just using one of the base kernels by itself. Think of it like mixing paint. Mixing blue and yellow makes green. It's not the same as just having blue or yellow. Nope, this is incorrect. A very large length scale for the RBF kernel makes the RBF part behave almost like a constant, but the linear kernel's influence still remains. It's still like having a ruler and a very flat piece of wood. Both are still contributing to the construction. I agree. This is correct because the product kernel combines the abilities of both kernels. It can model both the curved relationships captured by the RBF and the straight line trends captured by the linear kernel. It creates a much more flexible model, capable of fitting more complex data relationships. This statement's partially correct because it successfully highlights both linear trends and smooth relationships. But there's a slight inaccuracy because neither the RBF nor the linear kernel inherently models periodic, repeating, patterns, and their product doesn't create periodicity out of nothing. This refers to a statistical method, Gaussian process regression, using a more complex kernel function to improve the model's capacity to capture relationships in data. The word composite means that the model uses more than one type of base kernel, resulting in more modeling flexibility. I'm asking you this question to test your understanding of how composite kernels work in Gaussian process regression, GPR. We're using scikit-learn's GPR with the product kernel, which combines an RBF kernel and a linear kernel. Let's figure out what that means for the model's behavior. I want you to pick all the statements that correctly describe how our fancy composite kernel behaves in this scikit-learn GPR setup. This is Gaussian process regression, GPR, using a product kernel. Think of it like this. You're combining two different ways to understand your data. I use an RBF kernel and a linear kernel to do this. A special parameter called length_scale_RBF in RBF kernel is set to 2. This is a linear kernel. It assumes a straightforward relationship between your input data and what you're trying to predict, a simple, straight line, like y equals mx plus c, simple and elegant. This refers to the combined behavior of the RBF and linear kernels. The RBF kernel, radial basis function, captures smooth curves, while the linear kernel models straight lines. Together, they can model both smooth, curvy relationships and linear trends. The composite kernel, the result of our combined kernels, is more adaptable because it incorporates both the flexibility of RBF kernel and the precision of linear kernel. I can model more complex patterns in the data than I could with either kernel alone. Isn't that neat? This statement sets up the entire problem. We're using scikit-learn's Gaussian process regression, GPR, with a special type of kernel called a product kernel. This special kernel combines two simpler kernels, a radial basis function, RBF, kernel and a linear kernel. The goal is to understand how this combination impacts the model's behavior.